Hi, students. In this lecture, I am going to discuss problems. Let us see first one. A particle of charge q and mass m starts moving from the origin under the action of an electric field E naught I cap and magnetic field B naught I cap with velocity V naught j cap. The speed of the particle will become 2 V naught after a time. Let us see how to start it. Speed initially V naught, now it is 2 V naught, right? See how to start. So first write down the given data. Given electric field vector, it is E naught I cap. Magnetic field vector, it is B naught I cap. Velocity, velocity vector is, it is V naught j cap. So we have to find at what time speed becomes 2 V naught. So this is now given data. So both fields are along x-axis, velocity along y-axis. Now speed is becoming twice the initial speed. So after what time? So since we are knowing initial speed and final speed, we can find change in kinetic energy. Therefore, we can write here. So we can use net work is equal to delta K, which is nothing but work energy theorem, because we are knowing delta K. Okay. So here net work means work done by magnetic force plus work done by electric force, that is now equal to delta K, half m 4 v naught square minus v square, right? And we have learned that by magnetic force no work is done. This is equal to 0. That means now work is done only by electric force, right? So I am writing here. And see here, field is now constant. So since the field is uniform, electric force is a constant. Electric force constant means we can write work done by a force. If a force is a constant, directly F bar dot S bar, or this is multiplying magnitude of the force with component of displacement along force. So here S cos theta stands for component of displacement along the force. So here force is Q into E naught. This is now magnitude of the force multiply with component of displacement along the force. Force is now, we can say force is now along x-axis. So component of displacement, that is a half a t square displacement, because initially it was at origin. Therefore, x, I am writing here, initially it was at origin, right? Now we are focusing only displacement along electric field, means along x-axis. Suppose now it is x. Initially x is 0, now it is x. That means now x value how much? Half a t square. This is displacement of, sorry, this is a component of displacement along the field, or you can say along the force. So force into displacement component, that is equal to 3m V naught square upon 2, right? 2 and 2 gets cancelled. In the place of acceleration, see what we have to write. It is a q e naught, that is a force upon mass, right? Substitute here q e naught. This is q e naught by m into t square, that is equal to 3m v naught square. So from this t value, root 3, m into m square, it is now root, right? M v naught square, it is v naught upon upon what is left here, q square, that becomes q. E naught square, it is E naught. Okay. So root 3 m v naught by q E naught. So we have to focus that by magnetic force, no work is done. We know what is a change in kinetic energy. That's why we have taken work energy theorem. Right? So answer is now, it is option A. Okay. Let us see next problem. A particle of charge plus q and mass m moving under the influence of a uniform electric field EI cap and a uniform magnetic field BK cap follows a trajectory from P to Q as shown in figure. The velocities of P and Q are VI cap and minus 2V. This is actually J cap. Okay. So change this minus 2V J cap. Okay. Which of the following statements is, or which of the following statements are correct? So this is minus 2V J cap. Okay. So asked for 2 marks in 1991. See diagram. Electric field is along positive x-axis. This is now path followed, right? Initially speed was V. Now speed is 2V. Direction is along negative y-axis. This is y-axis. This is along negative y-axis. Okay. So we have to find strength of the field, rate of work done by electric field. Okay. See how to start. So first note down the given data. This is y-axis and this is x-axis. This is a path given. And you can see this is a point P. At this instant, direction of velocity. It is going along positive x-axis. Field is into the book field, and electric field is given, it is EI cap. And the magnetic field is, it is BK cap. And coming to here, this is now 2V at point Q. So first of all, we have to calculate what is strength of the electric field. So this is again same as the previous problem. Initially speed is known, final speed also known, means delta K is known, right? Therefore, we can write net work is equal to delta K. And by magnetic force, no work is done. This is only by electric force. Okay. Or if you want, you can write by magnetic force also. Total is now delta K. Now this is 0. So by electric field, Since electric field is uniform, electric force is also uniform, means it is a constant. Since it is a constant, we focus force into, force is now Q into component of displacement along force. And you can see here this is A and this is now 2A. So component of displacement. If you observe carefully, displacement how much means displacement S bar equal to along x-axis 2A. So 2A I cap along y-axis it is plus A into minus j cap. This is now displacement vector from P to Q, right? In this way. But we are focusing displacement component along electric field. It is 2A, right? It is 2A. That is equal to half m 4v square minus v square, right? So from this e value 4 minus 1 3 by 4 remaining is now mv square upon mv square upon it is qa, right? That is now strength of the electric field. Now remaining options, they're asking rate of work done by electric field. And we know rate of work done is nothing but power. And power is defined as, see how to calculate power. Calculation of power. It is F bar dot V bar. Okay. And you can see at P, electric field along positive x-axis. Velocity also along positive x-axis. Therefore, between these two vectors, angle is 0. Force is now Q into E into velocity, right? In the place of E. So the value what we got here, 3 by 4 mv square by qa into v. Q gets cancelled. 3 mv cube upon 4a, right? That is now power delivered by electric force at point P. And if you observe at point Q, field is along x-axis, but velocity along negative y-axis. Between these two angles is 90. So F bar dot V bar, it becomes 0. Okay. That means option D is correct one. Option B also correct. Okay. So see options. So A is correct. B also correct. Option D also correct. Rate of work done by both the fields is asking by both the fields. We are knowing that by magnetic force, no work is done. That means what is the power delivered by magnetic force? 0. By electric field, angle is 90. That's why by both the fields at Q is 0. So options are A, B and D. Okay. See next one. A particle of mass m and charge q is projected into a region having a perpendicular magnetic field B. You can see here cross. Cross indicates direction of field is into the paper or into the plane of the board. Okay, it is inwards. Find the angle of deviation of the particle as it comes out of the magnetic field if the width D of the region is very slightly smaller than 4 mv by 5 b cube. You can see here mv by b cube, that is radius of the circle, right? It is now 4r by 5. This is slightly less than r. This is r, right? mv by b cube. Slightly smaller than r. This is 5 by 3 times radius. Let us see how to calculate. Let us make a diagram. Field is now confined to only a particular region. Let us call field is confined to only this region. Field is now into the plane of the paper or into the plane of the board. This width is given as d. Let us take it enters now somewhere here. First observe here, velocity vector is in the plane of the board. See carefully, velocity vector is in the plane of the board, but magnetic field is normal to plane of the board. That means between V bar and B bar, between these two vectors, angle is now 90. And we have learned that if between these two vectors angle is 90, it follows uniform circular motion. Okay. So here the path will be, it is like this. Okay. This is a part of a circle. Okay. Now see what we can do. If we draw normal for this velocity vector at this point, so this line becomes normal for this velocity vector. Now draw normal for this velocity vector at this point when it is coming out of the field. Then see here. So taking normal, this is normal. Okay. So these two normals, they will meet at center of the circle. Take it as C. Now angle made by velocity vector while coming out of the field with initial velocity vector, that is now angle of deviation. Okay. If this is theta, this is also same angle, right? Because this is normal to this vertical and velocity is normal to this radius. And from this diagram, if you see, suppose this is here and this is now D. If you see triangle, right angle triangle, ACD, ACD, right angle triangle. From that we can write sine theta equal to D by R, where R is now radius of the circle. Okay. Now in this case, condition is D must be less than R. When D less than R, this value will be less than 1. Okay. In this, theta gives us angle of deviation. Okay. Let us see if D is not less than R. If D is greater than R, or D is equal to R. I am repeating. This is for D less than R. Let us focus D either equal to R or D greater than R. Okay. I am taking condition here. D is equal to R. See carefully. D equal to R means, so when this enters here, when it completes half revolution, So we should make a diagram very carefully here. Right. This is now semicircle. Semicircle. I have taken D equal to R. When it completes one-fourth revolution, when it completes one-fourth revolution, here still field is present. So this distance is equal to R, given D equal to R. So at this location also, that a particle is inside the magnetic field, means still magnetic force is acting on the particle. Therefore, it follows now subtler path like this and comes out of the region like this. This is opposite to initial motion direction. That means deviation is equal to 180. Okay. Suppose I'm taking D value greater than R. That means again same thing continues. Your condition is D greater than R equal to R. In both the cases, deviation equal to 180. Because when this completes one-fourth revolution, it is still inside the field only. Therefore, still magnetic force is acting. Okay. Suppose if we consider D is slightly smaller than R, slightly. See carefully this diagram. If you take slightly smaller than R, means at this point there is no magnetic field. Okay. When this completes one-fourth revolution, at that point there is no magnetic field. That means no magnetic force. No magnetic force means at this instant velocity vector is like this. This is now velocity vector at this instant. Now since slightly smaller than R, at this point there is no magnetic field, therefore no magnetic force. Therefore it continues to move like this only. That means in this case deviation will be 90. So you have to focus on these three cases carefully. D less than R, sine theta equal to D by R. So simply D less than R means this is less than 1. Directly sine equal to D by R. If it is equal to R greater than R, deviation is 180. If it is slightly smaller than R, deviation is 90. So regarding deviation, we have to remember these three key points. Okay. Now we can see here the given values. mv by bq radius 4 by 5. So it is a 4r by 5, which is less than r. So we can take sine theta equal to, right? Then how much we get? Sine theta equal to 4 by 5. That means deviation is approximately 53, right? It is now radius, slightly smaller than radius. So deviation is 90. It is a 5 by 3 times radius, which is greater than r. Then deviation is 180. Okay. I hope you got a clarity.